Hello everyone, welcome to the third episode of this masterclass dedicated to the configuration, calibration, pricing and risk of European equity options. If you haven't done so already, I would recommend watching the first two episodes of this series already available in the Trade in Analytics playlist of our YouTube channel. And as a reminder, everything is available and free to download on our repositories, the data for the examples, the spreadsheet, the code, everything really. So don't forget to like and subscribe so that we can continue to propose all this amazing content. It is starting to get slightly more challenging today as we tackle the equity forward curve construction. In chapter 1, we will start by looking at the EQCurve tab in the Excel spreadsheet, where the equity forward and equity volatility calibration are performed. I will explain the data structure, and I will also show you how to configure an equity forward curve in ORE with the curve config XML file. In chapter 2, we will be looking at the different types of equity forward curve configuration existing and the relevant market data which define them. In chapter 3, we will talk about the interpolation and extrapolation of the equity forward curve. And in chapter 4, we will do a deep dive into the algorithm used to perform the calibration of the equity forward curve from equity option prices, which is very much needed when we have multiple quotes for the same expiry. You will see. So looking at the EQCurve tab, you will notice that the design is pretty much the same as in the IRCurve tab. The button and most of the data at the top and on the right are related to the calibration of the implied volatility surface, which we will see in the next video. Today we're going to use this data here. Obviously we have the valuation date, the spot date is the same, the underlying, which is just there for information purpose, and the equity spot value for that underlying, which we will use in the calculation of both the equity forward and the equity volatility. So in the Excel, we have used a fixed 3 dates grid with one which falls on the maturity date of the current option, one that is 1 month before, and one which is 3 months after. No matter the type of input chosen, whether it's the call put options, as you can see here, the dividend quotes, or the forward prices, we have only used these 3 dates. But that's because I created synthetic market data in order to match these dates so that we have a sort of simplified spreadsheet because it's already pretty sophisticated as it is. So just bear that in mind. Then for each of these dates, we calculate all the interest rate related data, similarly to what we have done in the NPV tab, except that this time it's actually for 3 dates instead of 1. First, we have the time to maturity with the day count convention set to A365 because we are working in a continuous case like most of the time with discount factors. For each date, we interpolate the Ester discount factor curve, which are the rates we have bootstrapped previously in the IRCurve tab. So I'll show you where we have stored them. It's stored here. And if you want to know how we did this, there are 2 very complete videos explaining all this, which I would strongly recommend watching. You have the choice to use either the data calculated directly from Excel or the data coming directly from the C++, which are hard-coded here. Here we choose the C++ data just to minimize the differences with the calibrated data and option prices that we obtain at the end, but that's your choice. Then we get the Ester 0 rate from it. Then we add the 85 bips coming from the Ionia Ester spread, and from that we finally get the Ionia discount factors. As we mentioned in the first video, we make a distinction between the discount factor, which is used to discount cash flows from the payment date, and the forward discount factor, which is used to project cash flows by using its inverted value, so 1 divided by the forward discount factor. In our case, they both have the same value, and that is just so that we avoid having to bootstrap a second curve in the same spreadsheet, which will be an overkill. So that's it for the interest rate data, and it takes us to the main topic of today's video and one of the main inputs to the Black 76 model, the equity forward price. But to calculate it, in some cases we also need the equity dividend discount factor. In some other cases it is derived from it. We will see how it works in each case a bit later in the video. So let's jump to the Market Data Schemer tab, where we can see here how we configure an equity curve in ORE, although it's probably very similar to most existing pricing systems. If you watch some of the previous videos, the one with the change of collateralization currency video, you may recognize this Market Data Schemer. Just as a reminder, in an equity option, we have to configure 4 different types of structure: the discount factor curve, the projecting curve, which we refer to here as the forward discount factor curve, and which is the same as the discount factor curve in our case. So it's just interest rate, there's just one. And then the equity forward curve, which is needed by all equity instruments like equity forwards, equity options, equity swap, clicket, etc. And then the equity volatility, which is needed for all equity instruments with an optionality element. Today's video is just about the equity forward. The data for an equity curve is structured as follows. First, we have the today's market file, which is, let's say, the intermediate file between the equity option underlying in the portfolio file and the equity curve configuration in the curve config file. And then the curve config file defines the equity data quotes, which are needed and which we can find with the relevant prices or rates in the market data file. So really, in order to understand how the equity curve is parameterized, we have to look at the equity curve structure of the curve config file. And you can find some details in the documentation by clicking in here. So on the left, we have the documentation, and on the right, we have an actual example of a curve config. So first, we have obviously the curve ID, which we have showed previously and which should match what we have in the today's market file. Then you have the curve description, which is an optional node. It's just a verbose and just for information purpose. It's not used in any way. Then we have the currency of the equity, the forecasting curve. This is the discount factor forward in the equation, and it can be different than discount curve. As we said, it's not a case for us today. And this reference the yield curve, which is already been built in here. Then we have the spot quote. That's a reference to the equity spot price in the market data file. Then the type and the associated quotes node. These ones require a bit more explanation because ORE allows you to enter 5 different types of quotes, and we will explain those in the next chapter. Here, the one setup is the option premium, and we will finish with this one because that's the one requiring the most explanation. The rest of the fields in the equity curve nodes are optional and specify additional information on the quotes and interpolation, extrapolation of the equity forward and the dividend curve. So we have the calendar and the day counter nodes. These two are only needed when you provide quotes with the expiry in the quote expressed as a tenor instead of an actual date. And that makes sense, right? If you stipulate that your quote has an expiry in 3 months, for example, well, 3 months in different calendars or with different day count convention will yield different results. So when you provide a quote with the expiry date directly, well, there's no calculation to do, hence these fields are not needed, they're optional. For the rest of the nodes, which are related to the interpolation and extrapolation of the equity forward curve, we will have a chapter 3 dedicated to showing their effects, but this is how these nodes work. First, let's start with the extrapolation node. It's a boolean indicating whether extrapolation in the forward price is allowed, and it defaults to false. Then the dividend interpolation and dividend extrapolation nodes. These two should not be provided when the no dividend type is inputted. For all other types, this defines how the equity dividend rate is being interpolated and extrapolated. For the dividend extrapolation, same as the extrapolation, it's just a simple boolean indicating whether or not we want to extrapolate forward the dividend curve beyond the last date of the curve. And this will only be considered when the extrapolation node is set to false. If you set that to true, then the dividend extrapolation will be set to true as well. For the interpolation, similarly to the type of interpolation you can perform on any discount factor curve, you have 2 subnodes. The interpolation variable, it's the variable on which you want to do the interpolation, so either 0 for 0 rate our discount for discount factor. And you have interpolation method. This is the list of the methods which can be used, and we will take a quick look in chapter 3 on their effects. So now let's look at the first type of equity curve, the simplest type, the no dividend type. This one assumes that the stock doesn't pay any dividend, which means that our little qt in our Black-Scholes equation is equal to 0. So evidently, the dividend discount factor is equal to 1, and our equity forward price ft is simply equal to the spot price divided by the forward discount factor, which, as a reminder, are already been calculated before. And so for this one, all you need to provide as in terms of equity market data, that's the equity spot. Everything else is known. So it's very simple. And that's how it looks in the file. Like, as you can see, there's just the type node set to no dividends and no other data. All you need is the spot quote, and this is provided here. You'll notice that we still have equity option prices. This is actually used by the equity volatility in our setting for now. And if you want to price this option using ORE, you'll see that we added 2 new folders. If you look at this one, Alternative Equity Forward Curve, you'll see that we have 3 additional equity forward type. And we're going to use this one, for example, in our case. So no dividend, I'm going to price it. It's very quick. If we go back to the output, the NPV result will be found here. In the Excel spreadsheets, you can set it up to no dividends in here, and it will simply set the dividend rate to 0 for all quotes. So the discount factor is equal to 1 for the whole grid, and the forward will be simply calculated by dividing the spot by the forward discount factor. That's as simple as this. And once you've done the calibration, I'm going to skip that. You can see that the result is equal to this, and it matched exactly the result that we have in ORE. Then we have the dividend yield type. For this one, on top of the equity spot, you need to provide a series of equity dividend rates, or at least one dividend rate. From these 2 inputs, you can very easily calculate the equity forward price. You simply calculate the discount dividend factor first, and then the forward price is equal to the spot time the dividend discount factor divided by the forward discount factor. Looking at the market data schema, we need, obviously, as we said, ST, we need QTs, and we need the forward discount factor, which we already calculated previously. In terms of ORE configuration, the type node needs to be set to dividend yield. Then you need to provide a quotes node with an S, and then a series of quote nodes without an S. The structure of each quote needs to be equity underscore dividend, then a rate, then the underlying reference, the currency of the equity, and then the expiry date. Or, as we mentioned already, you can replace the date by tenor, and in that case, it is also recommended to add the day counter and the calendar nodes, just to be on the safe side. And you can see the dividend rate in the market data file on the right, which we obviously also find in the Excel spreadsheets, in the market data tab, in the alternative data section. You can see we have exactly the same values. And if we use ORE to price this equity option, we obtain, again, the same price as in Excel after calibrating the volatilities, of course. Then we have the forward price and the forward dividend price tabs. Both take as input the equity spot ST and explicitly, or directly if you prefer, the equity forward price FT. So no need to calculate them. However, in ORE, I will explain that in chapter 3, but the interpolation of the equity forward curve is done through the dividend data. So in order to calculate the dividend discount factor, we can just reverse the forward price formula that we have above, and voila. Alternatively, you can now calculate the dividend rate first, and then from it calculate the dividend discount factor, which is what we have in the Excel. Both forward price and forward dividend price work in the same way, but forward price is the one usually used. Forward dividend price is only applicable in the case where the index is an equity dividend future index, And in that case, it will be excluded from the SIM calculation as per the SIM methodology. So that's very specific to, you guessed it, the SIM case. In terms of market data schema, we have, as usual, the spot price, the forward prices, or at least one, and as usual as well, the forward discount factor. In terms of ORE configuration, the type node needs to be set to forward price. And then, as previously explained, you need to add a list of quotes. The structure of each quote is equity underscore FWD for forward, then price, and then the same as before. And you can see how it looks in the market data file. Those data are also found in the market data tab in the spreadsheet, same as before under the alternative data section. And you can see them, it's exactly the same value. When the equity curve type is set to forward price, those data are fed directly into the forward price cells. And as mentioned before, the dividend rate is calculated from it using the formula we've seen, and from it, the discount factor is calculated. And as usual, if we price it in ORE and look at the NPV results, both NPVs are exactly the same. And finally, we have the option premium type, which requires spot price and equity option prices. So both call and put option prices. And this is the configuration we are using for our pricing in this example, because that was the original configuration from previous ORE examples and for some of the oldest videos. Now, this is not that straightforward. I mean, it is if you have only a single quote pair, a quote pair being a quote containing both a call price and a put price for the same strike and for the same expiry date. In that case, you can simply use the call put forward parity formula to calculate the forward price and deduce the dividend discount factor from it. However, usually you have many quotes with different strikes for the same expiries. In our example, we have 3 different quotes per expiry, so with 3 different strikes. And this requires a sort of root finding algorithm, which I will explain in chapter 4 of this video. Please note that if a pair is not complete, it is discarded and it won't be used in the calibration. In terms of market data schema, we have the spot price, we have the call and the put prices, or at least one pair of them, and as usual, the forward discount factor. Regarding the ORE configuration, the type node needs to be set to option premium. There's an additional node called exercise style, which needs to be set to European in our case. Then you need to provide the list of quotes. The structure of each quote is equity underscore option, then price, then the underlying reference, the currency of the underlying, the maturity of the quoted instrument, its strike, and whether it's a call or a put with the letter C or P. And instead of providing an explicit list of quotes, you can also provide a wildcard, which replaces both the expiries and strikes and make things a little bit easier. And then you can see in the market data file how it looks like. We only have the spot and the option prices. Use both for the calibration of the equity forwards and the equity volatility. So it makes things a little bit simpler as well. As usual, this market data can be found in the market data tab in the Excel spreadsheet under the main section. Now, in order to imply the equity forward prices from these option quotes, you first set the equity curve type to option premium, and then it requires an algorithm which has been coded in VBA and which I will explain in chapter 4 of this video. But for now, I'm going to assume that we have calculated it already. In that case, it's going to be the same order of things as for the forward price case, where you calculate the dividend rate from it, and then the discount factor. And as usual, if you price this configuration with ORE and look at its result and look at the NPV calculated from it, it matches the one from the Excel spreadsheet. And one last thing I haven't showed until then is that if you set the additional results node to yes in the ORE file, you can access the additional results data. And here you can see the sort of intermediary values calculated. So for example, the forward, you can find it here, the dividend discount factor is here. You have the discount factor as well, which is here, and the volatility, etc. And that is it for the different ways of calculating the equity forward prices curve and the resulting equity dividend discount factor curve. In the Visuals tab, you can see the resulting curves we obtain when we interpolate the data points to the forward discount factor curve. You can see the data are coming from this table and the dates are coming from the relevant tenors in the IR curve tab. First, we have the interest rate forward discount factor curve on the top. Then we have the equity dividend discount factor curve with the 3 different scenarios of extrapolation, which we'll see later. And then on the right, we have the equity forward price curve, which start obviously at T0 with the spot price, and then the forward price goes down. And similarly, we have the 3 different scenarios of extrapolation of the dividend discount factor curve, which we will see also later. And that takes us to the subject of interpolation and extrapolation of the equity forward curve. It appears straightforward, but when you look at it in the details, it's not. So I figured I'll provide some insight in it. First important point to raise is that we don't interpolate or extrapolate on the equity forward price directly. We do it by interpolating on the dividend curve. So either on the rates, which is the case in the Excel spreadsheet where we do a linear interpolation on the dividend rate, or you can also do it on like a log linear on the dividend discount factor. And by doing a second interpolation on the interest rate forward discount factor curve. And that's, in our case, it's the EONIA curve. And from these two interpolated values and the equity spot, we obtain our interpolated equity forward price with this formula. So that's the first point. Second point, the range of expiries from the dividend curve where we apply interpolation and the expiry from which we apply extrapolation is dependent on the interest rate data quotes. And there's an adjustment of the boundaries being performed, not different from the process used to clean market data when you have a missing quote. So I'll explain what that means. So here on the left in green, we have what represents the list of expiries from the equity curve data, and on the right in blue, the list of expiries from the interest rate data. The first case we're interested in is when the maximum expiry from the equities, so Tmax EQ, is lower than the one from the interest rate, which is the most typical case, the interest rate quotes tending to be longer dated than the equity ones. So most often, and this is the case in our data we are using today, Tmax is equal to Tmax IR. And we also have T0 represented here. And it's worth pointing out that Tmax is capped to 50 years. That's an ORE quantlib feature, meaning that if the expiries from the interest rate data go beyond 50 years, which is the case with our data because we have a 60-year tenor, Tmax will be equal to 50 year. Now, you will be forgiven to think that the extrapolations parameter you can configure in the curve config file, so the extrapolation and dividend extrapolation nodes, apply to any dividend data out of its initial boundaries. But that's not the case, because in that situation, with boundary value of both sets of data are adjusted so that we can interpolate, not extrapolate, any values between T0 and Tmax. And in order to do that, a point is added at T0 to both the dividend and the interest rate data, and a point is added at Tmax only to the dividend rates. So we're adding 3 more points. The second case that can happen is when the quotes from the equity data are longer dated than the relevant interest rate data. In that case, same as before, a data point is added at T0 to both the dividend and interest rate data. And I would assume, I haven't checked the code to be honest, and that wasn't something I dug through when doing the OIS bootstrapping video. I would assume a similar point at Tmax is added to the interest rate data. Obviously, there's a third case, which is when a Tmax EQ is equal to Tmax R, but in that case, this scenario doesn't happen. So just to summarize, once we've adjusted both sets of data, the interpolation method you have set in the curve config XML file will be applied to any point between T0 and Tmax. And so we're doing interpolation in it. Any data past Tmax is then considered extrapolation. And those 5 quotes are the one we use for interpolation. So we have T0, we have the 3 quotes which we looked at here, and we have Tmax here. As I showed you previously, this is the list of interpolation types which is accepted by ORE in the context of equity forward time structure. I won't explain them in details and I won't advise on which one to use because this is really dependent on your data and that's a bit beyond the scope of this video. But we tend to use linear interpolation on the rates or log linear interpolation on the discount factors. I will, however, show you the effects of each interpolation on our current set of data so you can judge by yourself. Here, first of all, this is a dummy example showing you in theory the effect of each of them. Just so you know, it's not based on ORE, it's from SciPy, a Python library. So first we're going to look at the effect of interpolation when we have only those 5 points. So when we're interpolating using either the dividend rates or the discount factor rates. And the grid that we're using, that's the usual one up to 2071. So we're not doing any extrapolation here. It's just to show you the effects of each interpolation method. So on the left, we have the interpolation on dividend rates and on the right on the discount factors. And you can see, first of all, on the dividend rates, it's not very pretty. I mean, except the linear one and potentially the convex monotone or the log linear. I'm just talking visually, of course. All the more complex type of interpolations, they're not coping really well with a very small set of data. On the discount factor side, well, linear is all right, quadratic is all right, cubic spline looks fine as well, convex monotone and log linear. Cubic spline, log quadratic and financial cubic, it's not usable. The second case I'm going to show you is when we are using the results from the original data, which had way more call option prices, so up to almost 9 years. So we're going to use all those data and we're going to use, first of all, the same grid as before. Here you can see that we're doing a little bit better with the more sophisticated method. And the linear one, obviously, it's completely flat between the 9 years and a half, between the 10-year and the 50-year point. Quadratic, I mean, in terms of range of data, it's not too bad. You might want to choose such an interpolation method, depending on what you want to achieve. Same for natural cubic spline. Now, if you look at cubic spline and financial cubic, it's not great. Log quadratic, it's not completely not working. And then after we have convex monotone and log linear, which is all right. For the discount factors, linear here you can see we just go straight from the 10-year to the 50-year point. Quadratic and natural cubic spline, same as log linear and convex monotone, they're pretty nice. The rest is the same. It's not very usable here. Now, if we remove the sort of artificial points that we created at the 50-year point, where we just did a flat extrapolation on the rate, you can see here most method actually give you some reasonable result, except log quadratic, and that's valid for both on the rates and the discount factor. So log quadratic, I'm not too sure which cases this makes sense, but here clearly it's not applicable. Now we have two nodes, if you remember correctly, to parameterize how this extrapolation is performed, which creates 3 different scenarios. Scenario 1, the node extrapolation is set to true. In that case, the dividend extrapolation node is not considered. And here the documentation says that extrapolation in the forward price is allowed. It simply means that we're using the standard discount factor calculation method with a flat extrapolation of the dividend rate or div upper t, which is also equal to r div t max, which is, as we seen before, also equal to the dividend rate calculated at the last expiry date from the equity curve growth, so t max EQ. Scenario 2, the node extrapolation is set to false, and the dividend extrapolation node is either not present or set to false, its default value. In that case, no extrapolation is done. It is kept constant to the dividend discount factor calculated at Tmax. And finally, scenario 3, the node extrapolation is set to false and the dividend extrapolation node is set to true. In that case, we extrapolate forward at the risk-free rate between Tmax and upper T, which is this coefficient here. And you can see in the Excel that we didn't account for the different type of interpolation, so it's by default linear interpolation on the rate, but you can change the extrapolation and the dividend extrapolation parameters. Now let's tackle our last chapter where we go through the algorithm used to calibrate the equity forward from numerous equity options premium quotes. First of all, let's take a look at how the quotes are reorganized in the algorithm because it really helps understand how the rest of the algorithm will work. Let's assume that we have a number Q of quote pairs, each defined by an expiry date small tk and a strike upper K small k. Bearing in mind that the values of these expiries can be the same across multiple pairs. T1 can be the same as T2, which can be the same as TQ, etc., and same for the strikes. But each pair is unique. Now, each quote pair holds only two option quotes, which means we have 2 times Q valid quotes. A quote is valid only if you have a corresponding call and put price, which means that if for a given quote couple expiry strike, we only have a call price and not a put price, and oppositely, we only have a put price and not a call price, the quote won't be used because we simply cannot use the call put parity equation to imply the forward price. Now, let's reorganize these quotes by unique expiries TI in a chronological order, and then for each TI, store the strike associated with each expiry, also in chronological order. I'll show you a little bit later an example of it. We obtain a data table a bit like this, with which each TI, we have a series of key I and M. Here, it's worth noting two things. The TI in the second table are different from the TK in the first table, which is pretty obvious because we can have duplicated TK and they are not necessarily ordered. Secondly, M1, M2, MI, MN are not necessarily equal. Actually, they are most likely not equal because we usually have more liquidity, which means more quotes, for the short and medium expiries than for the long ones, for example. But please bear in mind that this table is just conceptual representation of how the data is stored by the algorithm. It's obviously not exactly like this. Now, if we take the data we are using today that you can recognize from the market data tab and transform them so that it fits our conceptual representation, first by grouping them into a quote pair, and from there we can extract the list of a unique quote pair. So we end up with 18 valid quote for 9 unique quote pairs. And from this data, we can produce the first table in the format we just talked about. Second step, by removing the duplicates from the expiries. So we keep 3 of them. And similarly for the strikes, so we keep 5 of them, while also ordering them in an ascending order. And from that, we obtain a sort of intermediary table, which is visually easy to understand, but not very efficient when dealing with data storage in code, because we have a lot of empty values, as you can see. And we generally prefer using lists or collections, which have a size equal to the number of elements it is composed of. And so that's how we obtain our final table here. And from there, the algorithm will loop through every expiry and then apply the algorithm I'm going to show you. Now, according to the non-arbitrage property, for each expiry TI, we should be able to calculate the exact same equity forward FT regardless of the strike K. And we have here the forward call put parity formula. If we discretize on each quote pair, we obtain a formula which looks like this. And you can see that each forward is dependent on both I and G, same as for the strike, obviously, and the call and put price as well. The forward discount factor, on the other hand, is unique per expiry. And the forward price should be as well. We should have FI1 equal FI2 equal FIG, etc. But that's the theory, because in practice, that's not exactly true, at least for a certain level of precision. And just to illustrate that point, you can try and calculate the equity forward using the forward call put parity formula and the data from our example. You can see that the forward we get from there are close, but they are different from each other. So the question is, for each expiry, which F do you use? How do you calculate the best estimate for the equity forward? Well, we can use a derived arbitrage property formula, which says that the forward price of the asset aligns closely with the strike price if the call price and put price are nearly identical after readjusting for the discount factor. So if this element is equal to 0, and that's basically when the option is at the money forward ATMF, which means we need an algorithm to find the estimated K little hat such that the call price minus the put price adjusted for the discount factor is equal to 0, or at least sufficiently close to 0. And we have such an algorithm in ORE, which I'm going to explain now. So the algorithm has two main steps. Step 1, the initial guess, and step 2, the refinement. And like I said, this is for a single expiry. So we'll have to loop and repeat this algorithm for every expiry. So step 1, the initial guess calculation phase. Here, we make a first guess at the forward price by taking the midpoint of the two strikes from the quotes, which should be around the at the money forward value. And to do that, we iterate through all quote pair for this expiry from the lowest strike to the highest strike, and we stop when the call price become lower or equal to the put price. When we find that strike, we take the middle point between this strike and the previous strike, and that's our initial estimate for the at the money forward price. There are two special cases. If we don't find any put price with a higher value than its corresponding call price, that could mean that we are in a very bullish market. And in that case, our initial guess for the forward price is set to the highest strike from our quotes. In the opposite case, if no call price is higher than its corresponding put price, which you can find in distressed market, for example, our initial guess is set to the lowest strike from our quotes. So very simple so far. And if we look at the synthetic call and put price surfaces, which you can find in the NPV tab on the right, we have this column which is compare the difference between the call and the put price. And you can see where it becomes negative here. And if you select the value between the two strikes, around that, you have a 4075 value, which to be fair, is not that far from the equity forward. So, but just as a reminder, that's just an estimate value for the initial guess. And now step 2, the refinement phase. This is where we try and find the strike such that the call price and the put price are nearly identical, obviously after adjusting for the discount factor. So the goal that we established before is find K such that the difference between the call price and the put price divided by the discount factor forward is close enough to 0. So reminding that this is the equation for the forward call put parity, we can replace the strike value by discretize value of the forward price, because after all, it's all just a notation, and the equity spot, the equity forward, and the strike are on the same axis. Now, after setting the value of our first iteration to the initial guess we calculated in step 1, and then if we consider that the equity forward value is the next increment at k plus 1 of our forward price at increment k, we obtain an iterative process which adjusts the forward value at each iteration. It's worth pointing out that at each iteration, we most likely have to linearly interpolate our call and put prices, which is going to be done on the strike axis, using all the call prices at the specific expiry to determine the interpolated call price, and all the put prices at this specific expiry to determine the interpolated put price. So we have our initial condition, we have our incremental calculation formula. All we are missing now is our exit condition, and we have two. The first condition, which is the one we hope to reach, we exit when the relative difference between the two incremented forwards is less than 0.1%. And that's because when that's the case, it means that the next incremented value is very close to the previous one, which means that this element of the equation, call pro minus put divided by discount factor, is also really close to 0, which means that the algorithmic non-arbitrage property, which we talked about earlier, is met. The second condition is when k reach 100. And this condition means that we're not really converging well, usually, and it's to stop the algorithm looping forever. One last thing, there are also two special cases which happen when the incremented forward value is overstepping the boundaries of our quote strikes on either side. And then in that situation, we simply calculate the forward price at that boundary. And I will finish this video by briefly showing you the Excel VBA implementation of this algorithm and its corresponding C++ implementation in our library. As a reminder, this function is called in the EQCurve tab, where we want to calculate the equity forward price, surprisingly. It calls the function estimate best equity forward, which takes three inputs: the expiry date, the forward discount factor, and the numerical data from the core put option quotes in the market data tab. The function is implemented in the module mod EQFWD calculations and is composed of three different steps, and the steps are the ones I've explained to you just before. We have the data collection, we have the forward guess estimation, and the forward calculation and verification, which is the refinement step. For the data collection, we loop through all the quotes data, which we transform into an equity option quote object. In VBA, it's called in a class module object, where you can define get and let property functions along with any specific behavior for that particular object. And here, if the expiry date of the quote matches the date we've passed as input, we add it to the relevant collection, so either call or put call. And the rest of the lines here, they are just here to make sure that we're inserting them in an ascending order. In the C++, it's not that obvious where this operation takes place. So we have the collection phase, the parsing phase, which happens in the EQCurve class constructor. Here it's reading the quotes in the option premium case and parsing the data, making sure that there's no duplicate. Then later in the function, it is creating the association between the call and put quotes at the same expiry strike pair. And then later on, in the initialization of the option interpolate to the class, it orders the expiry date by ascending order. Here it's done directly by the std set object, which automatically sorts the element and remove duplicates. And then later, the strikes are ordered with the sort function. Back to the VBA, for the second step of the algorithm, the first guess estimation, we simply loop through the list of quotes. And when the call price becomes less than the put price, we exit the function and return the middle point between the two. In the C++, it is called line 364, still in the EQCurve class constructor, and it is called the first time we are asking the equity forward curve stripper object to produce some outputs. And then it triggers the calculation. And you can see here it looped through the list of unique expiries, and for each expiry, it calculates here the initial guess. Which is very, very similar to the one we have implemented in the VBA. And finally, step 3, the refinement. We have our loop with the two exit conditions. Case 1 and case 2 correspond to the special case where the forward has reached a value which is outside the boundaries of the strike from the quotes. In that case, we calculate the forward with the forward call put parity formula and exit only if the value is still lower or higher than respectively the lowest strike or the highest strike. Case 3 is the typical case. Here we prepare the data for the linear interpolation. If it is the first time that we reach that stage of the algorithm, with the strike representing the x-axis and the call and put prices representing the y-axis. And then we linearly interpolate the call and put price at the current value of the forward and calculate the new forward using the forward call put parity formula. And obviously we exit if this new forward has a relative difference with the previous forward, which is less than 0%. And you can see in the code, It's really just the same as in C++, so it's very easy to follow. And that is it, really. This video should give you enough basic knowledge to build an equity forward curve. And in the next video of this masterclass, we will tackle the calibration of the equity volatility surface. And you will see that similarly to the equity forward curve, there are multiple ways to build it. So don't forget to subscribe to be notified when it goes out. See you next time.